Thank you for joining us for our last Science Friday of the year. We will start up again the first Friday in April. If you are lucky enough to join us in person, we do have some refreshments thanks to our friends group. They've been very generous all year, providing us with some delicious refreshments. So incentive, if you are virtual today, if you come back in April, there'll be refreshments. Today we are joined by Dr. Jeff Pugh, who is currently a postdoctoral research at the University of Minnesota in Duluth, but was previously, come on and join us, previously with the Cleveland Water Alliance, and was involved in water quality research, obviously here at Oldham Creek and in Lake Erie as well. So I'm going to turn it over to Jeff. If we have questions along the way, Jeff, I'll let you know. Otherwise, we'll try to save our questions for the end. Works a little bit better in this hybrid format. All right. Thank you, Jeff.
Thank you. Yeah, first of all, I just want to thank Oldham Creek for inviting me to talk about what I did back before August for 3 years as a postdoc at Cleveland Water Alliance. This is kind of still wrapping up research topic that concerns with some of the water sensor technology innovation that I did kind of was connecting both my work at Cleveland Water Alliance and also Oldham Creek, both science and technology work. So without overview here, just a little bit about myself. I was trained mainly as a environmental engineer. I got my bachelor's, master's, both in environmental engineering. My PhD took me to upstate New York, where I did a lot of remote sensing of water resources. And then I began my non-traditional, quote unquote, postdoc at Cleveland Water Alliance. And that was initially a three-way funding from Cleveland Water Alliance, NOAA, and the CIGLR, which is the Cooperative Institute for Great Lakes Research, where I did a lot of sensor implementation, deployed around 13 different buoys in Lake Erie, and then work with a variety of different technologies. So I'm going to show you some of that that I did at Oldham Creek. And now I'm in Duluth, up north, from the shallowest Great Lakes to now the deepest. And I'm doing more postdoctoral research at the Large Lake Observatory, focusing mainly on kind of winter limnology work now. So just some background. The more I get to do work at Oldham Creek, the more I'm fascinated about Oldham Creek. Oldham Creek is obviously a very dynamic system. On the left, you can see a satellite imagery from 2017 to 2025, around roughly 8 years of cloud-free imagery, monthly-ish. And you can see it's just such a dynamic system, all the way from the lake into the watershed. You can sometimes see, in the estuary, the water level changes from really high, submerging everything, to really low, where you can clearly see the river channels going through. And then at the beach area where the connection to the lake, you can also see it's a very dynamic system. I was taken away by speaking to Steve McMurray about the beach opening, and just fascinated by how dynamic it could be. Just like within a day or 2 day period, it can be opening or closing. And then the other dynamic part of this is the water level. And as you can see, this is the area right near where you are sitting. There is a kind of small stream discharge area, which also kind of consider as a wetland area because sometimes this area dries up and have vegetation grows in them. So that area is also super dynamic. This you can see through a kind of biannual basis of these imageries. You can see the water level either goes really in the up in the watershed, or it comes down. So some years have tremendous amount of flooding happening, and some time it does not. So it's also a very dynamic system. And so within these dynamic system, we would require a lot of information to kind of monitor them and to understand the different processes. And that is my perfect segue to a recent publication just published last year. And this was just looking at the area, which is pointing towards near where you're sitting right now, looking at the kind of temperate wetland dynamics. And what was found was that the amount of water level present in that area controls the amount of methane and also carbon dioxide release. And what was really interesting is when the water level is fully submerging the area, there is less amount of carbon dioxide being released, where compared to if it's partially flooded or if there's no water present, there is a release of carbon dioxide and there's less release of methane in that area. So this again kind of emphasized the importance of monitoring water level in that area and maybe even the entire watershed in general. So this is where the kind of technology piece comes in. And I'm going to just give you some background on this. Traditionally, we monitor water level, water quality with very expensive sensors. And this has always been how it is. And the amount of knowledge and training required to operate these also are tremendous. And the thinking here is that because these instruments are very sensitive and very accurate, um, the logical way is to have them become very expensive or have kind of PhD level or even higher to operate these systems. The obvious problem with that is it is really hard to scale up. And also, if uh, the equipment are broken, you will need to spend a lot of money to repair them or replace them. So here is a USGS map of all of the stream gauge locations across US. Obviously, on a national scale, looks great, all the coverage across. But if you start to zoom in, if we are looking at Almond Creek, there is only one gauging station by USGS in the old Woman Creek watershed. And obviously there are two more by Woman Creek south downstream of that stream gauge, but upstream of the that stream gauge you're looking at is not very well gauged. And so going back to the point that even though we are looking at a very kind of robust network of stream gauge, but when you look at finer scale, we are starting to have problems. And oftentimes researchers have to, rely on stream gauge that's far away to predict where they are looking at. So that's creates kind of a research scientific problem, but also a monitoring management problem. So I'll be very careful with this slide. It's kind of very technical. I'm just gonna breeze through this so you don't have to worry about all the details. So I'm just talking about some of the technical innovations that we can now consider and implement into our monitoring considerations. So the first one I want to introduce to you is a network that's called the LoRaWAN. This is very similar to kind of cellular Wi-Fi network. It's just a different type of network that was initially designed to transmit very long range, such LoRa, long range network. And the benefit of this network is use very little power, and it can transmit very long range, 7 miles or even more. And that creates a kind of prime opportunity for water resource monitoring to utilize this technology and to create networks that are both cheaper to maintain because it requires such little power. You can just put a battery in there and the battery will last for years. And the other benefit is you can save your money by set up a base station somewhere and having that base station communicate with hundreds of thousands of sensors within miles to communicate with that. So the cost saving obviously with that is you don't have to set up individual cellular plan or Wi-Fi plan for each sensor, which dramatically drive up the cost. So LoRa is, in a short summary, that's all the benefits that with that. And the other thing that's happening in the technology world we are all very familiar with is the miniaturization of technologies. Everything is becoming smaller and smaller. The phones can now fit in your pocket. And then there's other technologies that's also happening. So similar things is also happening in the water resource monitoring world. As you can see, this is just one typical example of monitoring water level. A USGS grade sensor at $4,000 is now, over years, it has been reduced down to around $1,500, $2,000 range. And then now there's new generation of sensor that come out only cost, $100 to measure this exact same parameter, which is water level in this case. And USGS, many state agency, federal agency has been adopting this kind of cheaper cost version as well. And this is actually what Almond Creek folks use as well. And this is essentially a radar sensor that measures water level. And for my talk, I'm going to focus more on this $100 one that we tested at Almond Creek. And from a scientific perspective on this technology front, there was a research published, not recent now, this is 2019, that looked at different scientific fields that utilize these low-cost sensors. And just by comparing the number of publications here, the water resource technology, the water resource monitoring or science research area has definitely been lacking behind. Comparing to air quality research or meteorology research, there has been a lot of use of those low-cost networks. And now there are a lot of different, whenever you hear like Internet of Things or IoT, those fancy terms, those all kind of relates to these low-cost sensors. They rely on telecommunication methods such as LoRa to transmit real-time data, and then they integrate themselves with a variety of different sensor types. As you can see here, these are different sensor types that all measure water level. Some of them measure water quality as well. This was done at Liminal Tech in Ann Arbor, which I worked with them as well. And they were testing different water level, low-cost water level sensors that use LoRa transmission. And as you can see, there are many different options out there right now. And it's sometimes overwhelming, but I'm here to kind of help guide some of these process. So it's not overwhelming at first to learn about these, but also part of my research focus on, how accurate are these things, how reliable are these things, and those are kind of the fundamental research question here. So for this project, I worked with Limited Tech folks and Cleveland Water Lines to build this um, system that utilized LoRaWAN and some of these low-cost sensors to have established basically a system that's real time, both utilize the low cost benefit, but also the low power benefit as well to measure a variety of different things. And this one in particular is focusing on water level. And then we kind of upload some of the data into our private um, data set database in the cloud, and then we can visualize all that data to just do a trial comparison of this sensor. And then some of these benefits I already mentioned, the batteries can last for years, and then the sensor themselves are cheaper compared to traditional approach. So these are the 3 sites that we install these low-cost sensors. And as you can see, these are all co-located right next to state-of-art approach. The first 2 up here are the Almond Creek monitoring site, and then the upstream, that's Sperling Road, which is right next to the USGS gauge. And then that's just a photo of showing you the different conditions that the sensors are monitoring. Obviously, you can see there's a difference of the river channel width monitoring here, and that creates a good kind of different environment that we can conclude from our results. So I just want to show you some of these comparison results, both using the actual time series, so comparing over time, and then some of the statistical tests. And I promise I won't bore you to death with that. And also I'll show you some of the reliability tests of the battery longevity, those kind of things. So this is looking at the Route 6 bridge site. Um, so the graph on the top, this is the water level of both the NERS water level measurement, which is in red, and then the blue is the IoT sensor, the low cost sensor. And then the above graph shows the over time what the both sensors are measuring, and then the graph down below is the difference between the IoT sensor and NERS sensor. So as you can see, majority of the time, the low-cost sensor matches up very well with the NERS sensor. And there are times where the measurements are off, and I'll get into that a little bit later. And those are mainly due to some pesky spiders that loves living in these sensors. So that's one of the kind of maintenance issue that goes along with this type of sensor. And then I just want to emphasize these difference that's kind of around the 0 point. That's just 1% of the data record. And just want to show you this is a very small percentage of the amount of data we are measuring. And then the other thing that's interesting or not interesting point out here is you can see the NERS sensor actually had some issues and was not able to measure the rest of the year. This is 2023 data. And the IoT sensor was there able to provide some data to support some of these measurements. Moving upstream, this is Darrow Road, and we actually have very good match between the NERS data and the low-cost sensor data. And this side, we pretty much have very minimum problem with spiders. Very, very fortunate. And there are still some data points that are mismatching. As you can see, some of these difference are above 0. But still, again, the percentage of the difference is fairly small, at 9% here. And when we move up to Berlin Road, we began to see some messy stuff happening. And you can see this is a site that I'm sure you are very familiar with it. If you have been to the site, this is a very tall bridge that goes under the valley. And mounting the sensor was difficult because we have a kind of maximum threshold for these ultrasonic sensor to be mounted. And initially, we mounted the sensor right on the I-beam of the bridge, and that actually was not successful. It was the measurements were going up and down all over the place. And then we kind of innovate and extended kind of lower to much closer to the water surface, and we can begin to measure that at least. But still, the noise, you can still see that through. So this definitely tells us there is a kind of maximum height where the sensor can be installed. And this side, I made a typo here. We're comparing USGS to the IoT sensor. And some of these difference you're seeing that's kind of all over the place here is definitely derived by some of these extreme height of mounting of the sensor. But obviously more analysis is needed to kind of identify these difference and then potentially remove them. And I have a QA/QC algorithm that I've developed to help remove some of these noise for the next step of this research. And then you can see definitely there are a lot more difference in this record. That's more than 0.1 foot difference measured. So going into statistics, I apologize for those of you who don't like statistics, but statistics is a very helpful tool in the toolbox in science, at least to help us understand if, especially in this case, comparing two different data sets, whether they are the same or they are different. So one way of comparing that is using correlation, and you can see this. Basically, the tests give us a number, and then based on the number, we can say, oh, if the two data set are completely the same, which is the 1 or -1, or it's completely different, which is the 0 value, that means no correlation. The reason why there's a 1 or -1 is sometimes a data set can be positively correlated. So one data is going up and the other data is going up. And then the other one could be negative, which means one data set is going up and the other data set is going down. So hopefully that's a very short understanding of correlation. And then the other statistics that I use is called t-test. This is one of my very favorite statistics that has a very interesting background story that I'm going to take you a little bit detour. And if you want to read more about it, there is a Scientific America article if you scan the QR code on that. So t-test is basically invented back in the days when Guinness, the brewery in Ireland, was trying to quality control their brewery, the beer products, and they were trying to find out a way how can they compare the different beer that's being produced and control the amount of quality in the beer. So they've produced a distribution, basically a statistics graph here. And so if the beer sample that they produce, they can compare again. So let me take a step back. So they've take a sample of all the beer that produced and then kind of determine the amount of quality of that beer. And then they found out this interesting pattern where majority of the beer are good quality that falls in the middle, which is the ideal kind of quality. And then if the beer is bad, it can fall in on both ways, whether the beer has too much hop or too little hop in it. So this is a really great tool now because you can now produce a beer and then compare that against this distribution, and then it can give you kind of the probability of how good your beer is. Um, and so this was initially produced by uh, basically researchers at Guinness, and it was named after them as the student T test. And then this is a very good tool for that because in my case of research, I can compare the two data sets together, where one sensor kind of provides one set of distribution, the other provides the other distribution, and you can compare those distribution to see if they are indeed from the same measurement or they are measuring the same thing. And then the main takeaway here is at the end, it will give you a t value. And if the t value is above 2 or below -2, it means they are not, you are not looking at the same sensor measurement. So that's one kind of very quick detour um, and going down my rabbit hole of statistics with beer stuff. So back into my results using statistics. So we'll just talk through each one of these. Route 6 is majority of the measurements when we compare the nerve measurement, which is on the x-axis, and the y-axis is the low-cost sensor. We can begin to see the correlation is 0.37. And that's mainly due to a lot of these sensors that were measurements were covered by spiders, and a lot of these measurements were off. That basically the local sensor is saying there's no measurement, but their measurement saying there is water level, which is the truth in here, the relative truth in here. And the t-test also give us a mean difference as well. And I actually forgot to put the t-value on here, but this t-value was around 12. So it means it is outside that t value. But still, I'm really hoping that if we remove these offset, we can get a better t value to justify the measurement of whether the low-cost sensor is the same as the standard sensor measured by NER. And at Darrow Road, when we graph this correlation graph, we can see the correlation is at 0.67. Everything falls on this red line. And one thing I forgot to mention here is the red line is the kind of correlation when it's 1, which means like a perfect, the kind of perfect measurement of the low-cost sensor compared to the standard sensor I'm compared to. So the fact that we're seeing a lot of these data are around the red line tells us it's had a very good result. And Berlin Road, as I mentioned before, majority of the sensor measurement does match with the USGS data, but there are still issues where some of these measurements are being affected. Interestingly, we can see majority's difference concentrate below this 10-foot measurement, and a lot of these are indeed um, impacted by the height of the sensor because it mounted so high. Some of these interference is definitely coming in through that measurement. So with the comparison, then the next step, we also ask about how durable are these sensors in terms of the battery. So looking at these are several battery voltage measurements that I did for these sensors. As you can see, the battery can definitely survive around kind of 2-year mark, but after 2 years, you probably need to change those batteries. And if we graph kind of the winter, summer temperature difference, this is definitely reflecting that pattern where in the winter it goes extremely low, and then in the summer the battery temperature goes back up. Um, and I just want to also mention that we deploy some of these in Michigan, kind of near Lake uh, St. Clair, Lake St. Clair, and they were able to survive kind of winter storm on the lake with no problem. So we were really happy with kind of the durability of these sensors to survive kind of extreme winter storm conditions or extreme summer conditions as well. So what does all these mean? What are the implications of this? For one, it's kind of very interesting is using the water level measurements through the low-cost sensors. We can be able to look at, based on the channel different geometry here, comparing all the different locations, you can see the amount of water level changes due to the amount of water that's being raised in those different channel types as well. So this is just a very simple kind of implication of this. The one possible extension from this is to, possibly implement or deploy a bunch of these at different locations. Then we can be able to compare when the peak flow arrives all the way from the, the upstream to the downstream at different locations to be able to have better spatial resolution or spatial understanding of where the water is flowing and the timing, the magnitude, all that interesting stuff. The other thing I want to touch on here is the kind of potential for opening this up to citizen science, possibly, or other large-scale water resource research, now with kind of lowered cost. And then it can also be, complementing existing monitoring programs to have lower cost sensor backups, such as what happened at Route 6 I mentioned before. You could have another sensor, low cost sensor, right next to your standard sensor to have a backup set of data, so you don't lose data in case you have to repair them. And I've already touched on this already. With the lower cost, it kind of opens up different other avenues for other groups to come in to monitor water level, concern publics or citizen science, as well as for universities to expand their spatial research. I did a kind of very back of the envelope calculation here to show you some of these potential savings comparing to having a traditional setup. And then this is just give you some rough numbers. In 1 year, you could save like around $2,000 compared to traditional sensors. And then if you scale up the number of sensors, you can also bring a tremendous amount of savings here. So that's another very rough estimation of the amount of savings you could have if you are deploying tons of these sensors comparing to a classic approach. And then the other possible future work, I've thought about this a lot, and maybe it will become real someday, and is to potentially, now that this paper has published and emphasized the amount of importance of water level controlling the different gas flux in the wetland area, we could potentially deploy a lot more of these low-cost sensors to understand the water level dynamics in the wetland area to help us maybe quantify over that entire wetland area how much gas is emitting based on the relation that was already discovered. And then some more technology stuff. These are just more kind of bonus material um, of my slide, not entirely relevant of my talk. But I was really happy to see this drone deployment, which I initially kind of helped connect Almond Creek folks with some of the groups at University of Vermont, which goes out and measure water quality uh, right near the beach area of Almond Creek. And they were able to both kind of have a apparatus that mount on a drone that drops in the water and take water quality samples, as well as measure the water quality of the lake by looking at the lake surface. You can start to construct different measurements of pH, temperature, dissolved oxygen, all that different important information. And this is still a very active paper that my collaborator are working on right now. So he's definitely working on that. And there's lots of interest generated nationally with different water resource managers are interested in using this, as well as research entities as well. And then the other project that I'm wrapping up as well is kind of integrating a lot of the water quality data that's around Lake Erie. And all these different dots you see are real-time water quality measurement points. And part of my project is to collaborate with Heidelberg University, their National Center for Water Quality Research, and to kind of figure out how do we break down all of these data silos that different organizations have to kind of have everything in one place, and also start to analyze whether what's happening in the watershed can be related to what's happening in the lake. So looking at this system-wide water quality data. So this is also very actively ongoing as well. So with that, I just want to thank all of the funding organization collaborators, especially Almond Creek, for allowing me to install these sensors and test them out. And there's definitely opportunities to expand the usage of this. We had various entities that contacted us and that wanted to install these sensors. These are just some examples of what we collaborate with. And with that, I'll just turn into questions. Thank you for listening.
Thank you, Jeff. That was very interesting. I learned a lot about what's going on out there. Does anyone have any questions? We can go online to check. You can either put them in the chat there. Shimon is instructing them to write it in the chat.
I have a question.
Yeah, Jacob.
Jeff, are there any solutions to the spiders? Like, is there a way to prevent spiders?
Could you hear him, Jeff?
Yeah, yeah.
I think there's, oh, that's a fly.
When I was working on this, I think I told you before, Jacob, I try to sometime use peppermint. Just like have some like cotton balls that you can purchase and like soak them up with peppermint, and then like just stuck them in some of these like crevices of the sensors. That worked little bit. I didn't test it extensively. I wish I had the time to test it more, but in Ann Arbor, at least, we tested it and we had less spider presence there. So that could be a potential option. And then the other is obviously do like post-processing and figure out a way to remove these data points.
Were there any other wildlife interactions with them? We've had all sorts of stuff on some of our other sensors.
We had not at Almond Creek, fortunately, but at Detroit, some of the sites are mounted literally in the river stream. So not much like wildlife, but like when there is like high river flow, like literally huge chunks of tree will fall into the water and then just knock off over the whole setup. So those were some of the worries. I think actually the Erie Conservation District installed one near one of their constructed wetland project. I believe I might be wrong. It was installed and unfortunately it was also knocked over by big debris and now it's gone. So some of these installs, especially like in channel, are very uncertain, I would say. Like the bridge install at One Creek, though, all fine. But like the in channel, these ones with like fence posts are, I don't have super high confidence with these setups. Yeah.
Okay. All right. Any other questions? No? All right. Well, thank you so much for your time and all the work you did here, Jeff. Hopefully you make it back in person someday and we can say hello again. But for now, enjoy the Upper Great Lakes. And hopefully we'll see you all in April for next year.
Thank you all.